Hi, in this video I would like to explain Bernoulli's equation in an easy to understand manner. Before we get into the equation, let's look at the concept. A fluid is coming in from the left as shown by the yellow arrow, and it's flowing towards the right through that glass tube, which has got a broad section in the beginning and it narrows down in the center, and it again increases to a larger diameter towards the right. So the gas or liquid is flowing through three different sections. So let's put a manometer at the wider section. So there the velocity is lower and the pressure is higher. You can see the vertical red arrow. So that depresses the mercury in the manometer to a larger extent. As the gas or liquid flows through the center narrow throat portion, its velocity increases as shown by the long red arrow, but its pressure reduces, that's shown by the green arrow, and therefore the mercury rises in that part of the manometer tube. Once again, when the gas expands to the larger portion, it resumes its lower velocity. There are three important assumptions behind Bernoulli's equation and its derivation. Because the equation is all about the conservation of energy, the gas that comes in with the kinetic energy is assumed to be conserving its energy even if it changes into potential energy. Therefore, there is the assumption that there is no friction with the tube walls, so therefore there is no energy lost by friction. The second assumption is that the gas or liquid is incompressible and its density doesn't change as it flows through the narrow portion. The third assumption is that there is a steady flow of the gas. Now let's take a simple case of a stationary liquid as we develop the Bernoulli equation. The fluid is not moving in this tank, but the pressure varies from top to bottom. The potential energy of a particle at the top is mgz1. The potential energy of a particle at the bottom is mgz2, as shown on the sketch. Now, units of energy are joules or Newton meter. If you divide that unit of energy divided by volume, you get Newton meter divided by meter cubed, and you land up with Newton per meter squared. That's nothing but force per unit area, and that's pressure. That's why energy per unit volume translates into pressure of this liquid. Therefore, pressure at the top of that fluid is P1 equal to energy by volume, that's mgz1 by volume. Mass by volume is density, and that's how you get rid of the mass thing, and you get rho g z1, where rho is the density. Similarly, the pressure at the bottom of the vessel would be P2 equal to mgz2 by volume, that would become rho g z2. So now the pressure difference between top to bottom will be P2 minus P1 is rho g z1 minus rho g z2. Rearranging that, you get P1 plus rho g z1 equal to P2 plus rho g into z2. Now we consider a case 2 where we drop some coffee from a cup, and as the coffee falls down from level z1 to a level z2, its potential energy gets converted into kinetic energy, or its total potential and kinetic energy at the top converts into a different potential energy and kinetic energy at the bottom. Again, we don't consider any friction with the air, so there are no external losses. Like the pressure difference that we found in the previous case, here we are looking for finding the energy difference. So write down the initial energy at the top at the level z1. That would be potential energy plus kinetic energy, that's mgz1 plus half mu squared by use initial velocity. Similarly, the final energy at the bottom at level z2 will be mgz2 plus half m into v squared. So now we can find the difference in energies. Now we step into a more complex situation, case 3, where the fluid is having a flow as well as there is a level difference between 2 points on a streamline. So at the top, at the level z1, the cross section is wider and the fluid flows down, and at a level z2, the cross section is narrower. So the static pressure difference between z1 and z2 will be equal to energy difference by volume, same as what we saw earlier. Here we bring the concept of work done. Work energy equivalence says that the work done is equal to energy difference. So we get W by volume. Substitute mass by density in place of volume. Then you get work done equal to P2 minus P1 into m by rho. Now we are in the final stage of the Bernoulli equation derivation. Once again, use the work energy equivalence equation fully. On the left hand side, put work, that's W, and substitute it by P2 minus P1 into m by rho. On the right hand side, the energy difference will be final energy minus initial energy. As simple as that. The final energy is mgz2 plus half mv squared. The initial energy is mgz1 plus half mu squared. So once you write that, you will find that the m, the mass, cancels on both sides, and you get P2 minus P1 equal to rho g z2 plus half rho v squared minus rho g z1 minus half rho u squared. You simply have to rearrange it to put all the 1's on the left hand side and all the 2's on the right hand side. So you'll get, which is highlighted in blue color, P1 plus rho g z1 plus half rho u squared equal to P2 plus rho g z2 plus half rho v squared. That's Bernoulli's equation, and you have done it. Now let's apply Bernoulli's equation practically to the beautiful tube that we saw in the beginning of this presentation. At that cross section, the wider cross section of that yellow arrow, let the values be P1 rho g z1 and half rho u squared, and at the narrow cross section, the red arrow, let the values be P2 rho g z2 and half rho v squared. Now the tube is perfectly horizontal, so the level z1 is equal to level z2 for both the cross sections. The rho is constant because it's an incompressible fluid. That was our assumption. So the only things that can change are pressure and velocity. Therefore, at the initial velocity shown by u, the pressure is high, and at the final velocity shown by v, the pressure is low. In summary, the Bernoulli's equation is an equation of the conservation of energy for a flowing fluid. It works well for liquids as well as gases, and gases are also considered incompressible as long as their speed is much less than the speed of sound. I hope this video was useful to you. Thanks and have a great day.